Okay, in this video we're going to be going over some more things about differential equations. And so far we've seen Euler's method and slope fields, which were ways to sort of visualize or approximate solutions to differential equations. And when we looked at differential equations for the first time, we saw some ways to solve them using anti-differentiation, or if it was an equation like y prime equals y, then we saw a way to solve that. But any other sort of differential equation, we currently don't have a way to find the solution exactly. So the goal of this lecture will be to learn a new method for solving differential equations. So let's start by looking at the differential equation dy dx equals negative x divided by y. So this is not an equation we know how to solve using the methods we've covered thus far in class, but we do know how to visualize the solution using a slope field. This was actually one of your homework problems. And so it turned out that the slope field looked something like this. So it sort of went around the origin in circles. So we have some idea of what the solution to this equation should look like, even though we don't have an equation for it at the moment. Now let's take a look at this equation here. I'm going to do some operations on this equation, which are going to seem dubious at first, but it's going to turn out they're all can be made valid. So the first thing I'm going to do is rearrange this equation so that all the y's are on the left-hand side of the equation, all the x's are on the right-hand side. So when I do that, I'll get negative y dy dx equals x dx. And now, I'm a step ahead of myself, equals x. And now I'm going to do something which maybe seems a bit sketchy, which is to move this dx over to the right-hand side. Now, of course, dy dx is a notation which means derivative of y with respect to x. It's not a fraction. On their own, dy and dx don't really have meaning based on what we've discussed so far in this class. But I'm going to go ahead and ignore all of that and treat this dx as though it's just the denominator of a fraction and multiply it to the other side. So I'll get negative y dy equals x dx. So again, a very questionable operation, but let's just see what this gives us. Now that I have this, I can take the antiderivative of both sides, and I get negative y dy equals antiderivative x dx. So you'll notice that it worked out really conveniently. The dy and the dx that came from this derivative turned into the dy and the dx that we need in the integrals. And now I can take the antiderivative of both sides relatively easily. I'll get negative 1/2 y squared equals 1/2 x squared plus c. If I rearrange this equation, I'll get x squared plus y squared equals 2c, but that's just another constant, so I'm still going to call it c. And this is an equation for a circle, which is in line with what we expected from our slope field. Furthermore, we can solve this equation for y and get y equals plus or minus square root c minus x squared. And even though we arrived at this solution through some questionable mathematics, we can check to see, is this a solution to our differential equation or not? And it turns out if we calculate the derivative of this function by the chain rule, we're going to get plus or minus 1/2 c minus x squared to the negative 1/2 times negative 2x. And if you rearrange this and simplify a bit, it turns out this is indeed negative x over y. So even though we arrived at this through this calculation, which we haven't justified yet, we can check that the answer we arrived at is indeed correct. So this method that we use to solve this problem is known as separation of variables. And it works for what are known as separable equations. So a separable equation is an equation which has the form y prime equals some function of x times some function of y. So these functions could be anything, like in this case, f of x was equal to x, and y was equal to 1 divided by y. And so, g of y was equal to 1 divided by y. And so this is quite general, but the point is that we have to be able to split up the x's and y's into a product on the right-hand side, so I can bring all the y's over to the left and all the x's over to the right. So my general procedure to solve this will be bring the g of y over to the left, write it as g of y dy equals f of x dx, then take the antiderivative of both sides. And if you knew what g and f were, you could actually calculate those antiderivatives in terms of x and y like we did up here. And then you would rearrange your equation and solve for y, and that would give you a solution to your differential equation. So let's see some examples of how we can use separation of variables. So let's revisit an equation we already know the solution to. dy dx equals k times y, where k is going to be just some constant. So we already know the solution to this is a constant times e to the kx, but the way we found that initially was just to guess and then see that it worked. Now we have a systematic way to solve this equation. So we can bring the y over to the left-hand side. We'll get 1 over y dy equals k dx. Right? So the first step, we've separated the variables. All the y's are on the left, or the x's are on the right. We take the antiderivative of both sides. This tells us that natural log absolute value of y is equal to kx plus c. Now we want to solve for what y is, so we exponentiate both sides. We'll get absolute value y equals e to the kx plus c. And we can use properties of exponents to simplify this to e to the c times e to the kx. Now on the left-hand side we have a y instead of an absolute value of y. But we can see that the right-hand side does not change sign. So that means that the sign of this thing is going to depend on the sign of this equation, of this e to the c. Or that's not really what I want to say. Okay, let me say this. So absolute value of y is equal to y if y is greater than 0, negative y if y is less than 0. And so that means that on the left-hand side, we're either going to have a plus or a minus y. If we have a plus y, then we'll just get y equals e to the c times e to the kx. And we can say that if we rearrange this, then, what I want to say is that e to the c is just some other constant, so it's a e to the kx. If we had the minus sign, then we would just move the negative over to the other side, and we'd get y equals negative e to the c times e to the kx. And from these forms of these equations, this one is always positive, this one is always negative. So essentially, your y cannot change sign, so you don't have to worry about the fact that this is only valid if y is greater than 0, this is only valid if y is less than 0, because if y starts positive, it will always be positive, and if y starts negative, it will always be negative for this equation. So that means that essentially, we can just treat, in either case, the solution as some constant times e to the kx. And so, in the end, what we get is the solution that we knew we were supposed to arrive at, y equals a times e to the kx. Okay, let's look at another example of a separable equation. So, if we have dx dt equals negative 10 x minus 5, and x of 0 equals 2, then we want to solve this using separation of variables. So the first step, as always, is to separate the variables. So in this case, I am using different letters for my variables in the problem. I have x for my independent variable, t is my dependent variable, but the procedure is still the same. We want to get all the x's on the left, all the t's on the right. So we'll get 1 over x minus 5 dx equals negative 10 dt. We integrate both sides. And this gives us natural log absolute value x minus 5 equals negative 10t plus c. If we solve this for x, then after a little bit of arithmetic, we'll get x equals a constant times e to the negative 10t plus 5. Then we had our initial condition, x of 0 equals 2. And this implies, if you do, again, some arithmetic, that a equals negative 3. So the solution to our differential equation is x of t equals negative 3 e to the negative 10t plus 5. Okay, next I'd like to look at the equation y prime equals square root of y. Okay, so let's try to solve this using differential equation or separation of variables. We have dy dx on the left. We want to get all the y's over on the left, so we'll have 1 over square root y dy equals dx. Integrate both sides. We can see that 2 square root y is equal to x plus c, or in other words, square root y is equal to x plus c divided by 2. And so y is equal to x plus c squared divided by 4. So if you were to plot these solutions, you'd see that there are a bunch of parabolas which are shifted, like so. Right, so if we change the c, we shift this thing either left or right. So we get a bunch of solutions like this. But there's another solution to this equation which is actually more obvious than what we can do with this separation of variables approach. So if y is equal to 0, the equation just becomes y prime equals 0, but since y is equal to 0, of course this is true. So y equals 0 is another solution to the differential equation. And in fact, there are some other solutions to this equation besides just y equals 0. So I'm not going to go into those solutions because it's a little bit complicated. But essentially, you can take a solution by combining pieces of both of these to get a new solution. Some sort of like piecewise function that uses this one some of the time and this one other times. So the only point I'm trying to make with this example is that at the moment, we know how to solve this equation with separation of variables, but there are some solutions that we could miss potentially. If, depending on what sort of equation we have, it's possible that we might miss some solutions using separation of variables. And this is related to some differential equations theory, which we're not going to cover in this class. But if you take a class on ordinary differential equations, then you will learn why we ran into this problem on this example. Why square root of y has certain properties that, or more specifically, doesn't have certain properties, and that causes this sort of problem to occur. So I want you to be aware of that, but it's not a subtlety that we're really going to focus on in this class. Okay, one more example that I want to show you. What if we have something like y prime equals x minus y? So this equation is not separable, because remember, a separable equation, we have to be able to get all the y's over to the right and all the x's over, or all the y's over to the left, all the x's over to the right. And so because we don't have a product here, the only way we can really get y over to the other side is to add it. So we could have like y prime plus y equals x. But then if you think about what we did before, we'd have dy dx plus y equals x. And you'd want to move the dx over, but then you'd also have a dx with this thing. So you don't really accomplish what you wanted. You don't separate the y's and the x's out. So we can't solve an equation like this using this technique. So there are still equations that are beyond our ability to solve, but knowing separation of variables greatly increases the class of differential equations that we can deal with. Okay, so the last thing I want to do in this video is to give some justification of why separation of variables is okay. So remember when we were doing these calculations, we did some crazy things like treating the dy dx as a fraction and then integrating both sides and incorporating the dx's into the integral. And so notationally, this all works really great. It works out exactly how we want it to. But why is it okay mathematically? So let's suppose that we have a separable equation like dy dx equals g of x times f of y. So let's let h of y equal 1 divided by f of y, so that we can rearrange this equation as 1 divided by f of y, which is h of y, so it becomes h of y dy dx equals g of x, right? That's certainly valid. All I did is divide through by f. And now I'm going to integrate both sides with respect to x. So this is certainly okay, because if two functions are equal, then their antiderivatives with respect to x are both equal. So what we get is the integral of h of y dy dx is equal to the integral of g of x dx. Now I'd like to take a look at this quantity here. So suppose that capital H of y is an antiderivative of little h with respect to y. And what I'd like to know is what is the derivative of this capital H with respect to x. Well, since y is a function of x, by the chain rule, we're going to get the derivative of capital H, which is little h, of y of x. But then we have to multiply by the derivative of y with respect to x. So what does this mean? Well, if the derivative of capital H with respect to x is equal to this, then that means capital H is equal to the integral h of y of x dy dx dx. And notice that's exactly what we had up here. So in other words, this capital H is the same as the integral of little h of y dy, which is the same as this thing. So I can rewrite my equation like so. And if you take a look at this equation, this is exactly the sort of thing we were getting when we were doing separation of variables. We have an integral in terms of y on the left of 1 divided by f, and an integral of g of x dx on the right. So this is why this method works. Really what we're doing is we're integrating everything with respect to x, but then we're doing this clever change of variables essentially, so that the left-hand side becomes equivalent to an integral with respect to y. But it would be a bit annoying to have to write out all these steps every time. So that's why the notation was chosen cleverly, so you can do this sort of sloppy steps and it still all works out okay. So it's fine if you use this method as I initially introduced it, where you multiply by the dx and solve things that way. But I do want you to be aware that there is some questions about how valid it is, and they're addressed by this argument. So that's everything I wanted to say about separation of variables. So in future videos, we'll be looking at how we can apply this to solving some more differential equations.